let's try and go through and solve this now. We now are in familiar territory. The entire point of this expansion method, the entire point is to try to get a summation, because we have a whole toolbox for analyzing and determining the complexities of summations. So we are now in what I would call comfortable, with my quotes around comfortable, territory. So let's try and figure out how to deal with the summation. There's a couple of ways that you could do this. You could either try to find a closed form expression. We can do that by distributing the summation and using linearity. I am not going to do that. In general, you will have to bound the summation. So I'm going to tell you how to bound this, because in general, that is what you'll have to do. So let us bound this above and below. Bound above. This summation is not necessarily an easy summation, because we talked about this, but we have not seen them in a little while. This is a decreasing sum, meaning that the summand, as I gets bigger, gets smaller. All of our rules are minorly different for this. So our first rule was to replace the summand with the largest value. Because it's decreasing, the largest value occurs at I equals 1. So this is C2 of n minus 1 is the biggest value in that summation. This is not surprising. I'm going to show you that that's not surprising. If I go back up to my patterns, if I look at the terms I had, the biggest term was n minus 1. And then there are smaller things. So down here, when I replace everything with the max, as we typically do, it's not surprising that it is n minus 1 there. And then we have that plus C1 just loitering at the end. It is worth noting that that C1 is not within the summation. The C1 is outside of it. If we wanted to include the C1 inside of the summation, we would need parentheses to do that. So the first thing we did here is actually the same as the steps we've always done. We replace each term with the max. Each term with max. It's just worth noting that the max occurs at a different value. It occurs at I equals 1 because it is decreasing. So now we no longer have I inside of the summation. So we can take the number of terms being the top minus bottom plus 1, that's n, times the summand, which is C2 n minus 1, plus C1. So that's just simplifying the sum. And we can then make this bigger in a very convenient way. I can get rid of the minus 1. So T of n is less than or equal to C2 n squared. Plus C1 I'm going to make bigger by replacing it with C1 n squared. And having done that, we can factor out an n squared, and we get T of n is less than or equal to some constant C2 plus C1 times n squared. So this is our upper bound, is that it is in big O of n squared. We need to bound it below and show that it is also in big omega of n squared. So let us draw our conclusion really quick and then do our bound below. So thus, T of n is in big O of n squared. We now need to bound below. Bound below. To bound below, we are going to take the original problem, T of n was equal to this summation. Our trick for dealing with summations and bounding below was to split them in half. So let us split that summation in half. This is T of n is equal to the sum from I equals 1 to n divided by 2 of C2 n minus I plus the sum from I equals n over 2 plus 1 to n of the same summand, C2 of n minus I, plus our other constant that was just loitering at the end, C1. So this is, we split the sum. It doesn't need to necessarily be in the middle, but in the middle is often one of the easiest values. And then we drop the smaller sum. Because it is a decreasing summation, the smaller sum is the second summation. So I'm going to drop the second summation when I bound below. So T of n is greater than or equal to the sum from I equals 1 to n divided by 2 of C2 n minus I. And then I'm dropping the second summation. So the second sum is going to get dropped. I'm also going to do the same thing with the C1. Because as we could see when we bounded above, the C1 was replaced and it is a lower order term. So we can always drop those lower order terms. So we drop both of those things. We drop second sum, or smaller sum, and C1. After doing that, we then are going to replace each term with the minimum value. So T of n is greater than or equal to the sum from I equals 1 to n divided by 2 of C2 n minus the smallest value within that range occurs at n over 2. Why? Because it is decreasing, the smallest value will occur for the largest value of I. So the smallest term in the summation corresponds to the largest value of I. Having done this, I is no longer in the expression, so we can simplify it. So that is why that is a helpful thing. So this is replace each term with min. Each term with min. And now we just keep simplifying the summation. So this is T of n is greater than or equal to the top bound minus the bottom bound plus 1, which is just n over 2, times C2 times n minus n over 2. Well, that's n over 2. I guess we can collect together all of our like terms, and we get T of n is greater than or equal to C2 n squared over 4. And now that's a number times n squared. So thus, T of n is in big omega of n squared. And if it's in big O of n squared and big omega of n squared, I can conclude at long last for this problem that T of n is in theta of n squared. So that is my final conclusion here. And maybe just because we've spent so long in this problem, we will highlight the correctness of that. So we highlight that there. So notice these problems get quite involved as you go because the end product is a summation anyway. So we still need to do all the sort of stuff we've been doing for for loops at the end here. So this entire page pretty much is just old stuff from the previous videos that we've watched. And before that, we had a full page worth of stuff to identify some pattern and to try and determine this actual summation to analyze. So these problems in general can start taking a long time. So we're going to slowly get a little bit faster at them as we go maybe, but it is entirely possible these problems start taking a long time. It's just the nature of the beast, unfortunately. Notice that the methodology here was identical. What we did is we first identify a recurrence relation. So step 1 is write recurrence relation. So step 1, write recurrence. You then perform several substitutions. Perform several substitutions. After performing several substitutions, you identify a pattern. Identify pattern. This is when we try to write down that equation with k. After you identify a pattern, you choose k. Then analyze whatever you have. Analyze resulting. I'll write sum because in general it's a sum. And those 5 steps are what we've been doing the whole time. Depending on the exact problem, some steps may be harder than other ones. The choosing k is always going to be relatively straightforward. The other ones are usually a little more complicated, and depending on the particular problem, can be easy to hard or anything in between.